Hello, everybody. Hopefully, you've already finished your Chapter 6 test. If not, I would really recommend that you do that before we move into this. This first section is not going to be that much related to what we've been talking about, but you do want to definitely make sure that you understand how to do all of our dimensional analysis and our conversions. So this is Chapter 7. This is stoichiometry. I know it looks like stoichiometry, but it is pronounced stoichiometry. Hopefully you've also already watched that introductory video that kind of explains at least a little bit about what a mole is, and it talked a little bit about stoichiometry as well. But we're going to begin at the very beginning here. Let me get my little pointer going. Okay. So for section 1, we're just going to talk about moles. Those of you that have played any Banjo-Kazooie games will recognize this is Bottles the Mole. He is called Bottles because of his, gigantic glasses here. Completely unrelated to what we're talking about, but I wanted to make sure that these slides still contained all of my weird references. So now you should be pretty familiar with how we do math and chemistry, and you know how to make equations. We've already talked about how to do equations, so we're going to connect those two things together. But to do that, we need a piece. We need something that allows us to convert between an equation and the math, the actual math portion, something that ties them together. The mole is that piece. Now, we talked about moles back in the SI units. It was the SI unit of something. Hopefully you answered that in the question from yesterday. But the mole is actually very, very, very important to chemistry. It's probably the most important SI units on that list, even more important than grams. So if you remember from last chapter, moles are the SI unit of amount of substance. So it's amount of stuff. Now, if you watch that video, this is the explanation that literally everyone does. I would use a different one just to be cool, but it's just the one that makes the most sense. There's no reason to reinvent the wheel on this. A mole is kind of like a dozen. When you say 1 dozen, you're not actually telling me anything. Like if I walked up to you and were like, hey, what's that? And you're like, oh, a dozen. Well, that doesn't tell me anything. A dozen what? A dozen baked goods? A dozen broken dreams that you're holding in your hands? A dozen bottles of water? A dozen rolls of toilet paper that you just fought someone for in Walmart? Well, what does that mean? Same thing when you say a mole. You don't actually tell me what you're saying if you just say you have a mole, unless you're, again, talking about this guy. If you're talking about this guy, then yeah, you are telling me, I guess. But we're assuming you're never going to be actually talking about that. In the case of saying a dozen, you're telling me that there's 12 of something. When you say that you have a mole of something, you are describing 602 sextillion, 214 quintillion, 76 quadrillion of something. Or, as we'll usually abbreviate it to, like it says down here, 6.02 times 10 to the 23rd. That is going to be our number for a mole. So 1 mole of anything is 6.02 times 10 to the 23rd of that thing. This number is called Avogadro's number, and it was defined by this really, really attractive goblin-looking man over here, whose name, or full name at least, was Lorenzo Romano Amadeo Carlo Avogadro. You will have to tell me, Marina, how good I did with my somewhat Italian pronunciation there. He was an Italian scientist in the early 1800s. He did a lot. There's a couple of he has a whole formula named after him, and he was kind of in the same community and crowd as Antoine Lavoisier, who is the father of modern chemistry. I think they were too far year-wise apart to actually know each other, but he was in that same community of people who worked on science. As we kind of talked about, though, most scientists back then were just a bunch of rich white guys who wanted to do science as a hobby. So a lot of them just didn't actually accomplish much. The ones that did tended to accomplish a whole lot, though, because they were rich. They had the free time to just do that every day that they wanted to work on it. They didn't need to worry about bills or anything like that. So, just to give you some context on moles, this is one of the things that every science teacher, no matter where you go, just loves to talk about whenever they get to moles, is to contextualize the size of a mole. So we're just going to run through a couple of them. They used a couple in that video that I had you watch yesterday, but this is going to be the ones that I like. So 1 mole of rice grains is more grains of rice than has ever been grown since the beginning of time. Like if you went all the way back to whenever the universe was created, and then we allowed time to progress forward and forward and forward until rice was somehow created through evolution or whatever means you believe that rice entered this planet on. And then we counted and we gathered every single grain of rice that ever was grown on this planet until right now, we would still not have a mole worth of rice. Okay, that's pretty big. 1 mole of marshmallows, and we're talking about mini marshmallows, I believe, with this calculation. 1 mole of mini marshmallows would cover the entire United States to a depth of 600 miles. So you could have a 600-mile tall layer of mini marshmallows over the entire United States, coast to coast, Alaska, Hawaii included, if you had a mole of marshmallows. 1 mole of pennies, if it were divided up among the Earth's population, everyone would get 1 times 10 to the 14th pennies. And that's so much money that even if you spent $1 million a day, it would take you 3,000 years to use all of that up. Which means that if you were born with this much money, like if you were a baby when this magical ghost sky deity whatever thing gave you a ton of money, if you literally were just born and somehow your parents every single day spent $1 million of your dollars until you were old enough to spend it yourself, and then you spent $1 million of your dollars until you died, and because you're super rich, we're going to assume you die at a pretty old age, so we'll say like 100. You get a heart attack at 100 floating around in your jacuzzi or whatever. If you died at age 100, you would still have hundreds of billions of dollars worth of stuff. You would have not even spent a reasonable fraction of the fortune that you would have. This number is absurdly large. However, notice that I specified that it was pennies. If it was just money that got deposited in your account, obviously everyone would be happy. But if it was actually pennies, life would not be comfortable because that much pennies would actually cover the entire globe to a distance of 400 meters. So it would be 400 meters worth of pennies over the entire globe. Granted, that would also displace the oceans because they've fallen into the ocean, which would rise sea levels, which would cause a whole other problems, and we would also probably just die from all of them suddenly spawning on the planet anyway. But this is just to give you context. The mole is an absurdly large number. Now this is a video that I'm not gonna make you watch. This is just one that it will be on the notes if you want to watch it. It's just kind of another example of some other like scale things. I already gave you the ones that I think are the coolest ones though. Okay, so what's the purpose of a number? That doesn't actually like seem like a useful number. Like you wouldn't describe anything with that. If you remember when we talked about units, we said that units needed to be something that was practical and made sense. You wouldn't use like the mass of an electron to determine a person's weight. That doesn't actually make a lot of sense. But moles is actually super useful because all of the numbers on the periodic table are actually written in moles. Moles is a part of that number. So carbon, for example, if you have 6.02 times 10 to the 23rd, if you have Avogadro's number worth of carbon atoms, individual carbon atoms, that 1 mole of carbon will weigh 12.011. And you might be wondering, well, why isn't it exactly a nice number? Well, remember, we only really have round numbers if it's just a single atom. That number is also the average atomic mass. And when you have 6.02 times 10 to the 23rd, of anything, the amount of stuff is kind of going to be pretty consistent. You're going to know, okay, well, if most of them are carbon 12, but there's a couple carbon 14s, I have 6.02 times 10 to the 23rd. There's probably going to be whatever percentage exists in the real world will be represented in that 6.02 times 10 to the 23rd moles of carbon. It would be like saying, well, 50% of the people on the globe are men, 50% of the people on the globe are women. If you have a group of 5 people, they might all 5 be guys. That would be a reasonable thing that could happen. It wouldn't be crazy. But if you had 1 billion people on this planet and somehow that random billion people you were looking at, you would probably expect, because that number is so much bigger, that it would fall more close to the actual 50-50. So when we talk about large amounts of an element, so no longer just saying an individual atom, we describe this number, this 12.011 that's on the periodic table. That is not just the mass of carbon. That is the molar mass of carbon. This is the average atomic mass, so it's what an average atom weighs, but it's also what a mole of that element will weigh, 12.011 grams per 1 mole. For single elements, you can just take the molar mass, look on the table, and bada bing, bada boom. You got it. You're done. To determine the molar mass of a compound, though, you're going to have to add up the molar mass of each element involved. Just make sure you are good on the subscripts. So my example right here, I have manganese SO4. I'm going to give you a chance to think about what polyatomic that is, because remember, those are important. You do still need to know those. So what is this polyatomic? Sulfate. This is sulfate. So this is manganese 4 sulfate, because sulfate has a -2 charge, and there's 2 of them. So there's a total of -4 charge over on this side. To cancel that -4, manganese would need to have a +4. So manganese 4 sulfate has 1 manganese, 1 Mn, but this 2 goes to everything that's inside of here. So this is 2 times the invisible 1 that's here with the sulfur, so that's 2 sulfurs. And 2 times 4 of the oxygens is 8 total oxygens. So when you add them up, you have to account for all of those pieces. Now, here's an example problem. This is going to be the stopping point for this slide show that we're kind of putting on here. But I am going to upload a video of me with a hand cam where I'll actually work out this example. So we're going to determine the molar masses of lithium chloride and magnesium nitrate. I'll show you how to work through that. If you have any questions about the PowerPoint, or after watching those videos you have any questions, remember you're free to always email me, or you can put any comments on the box to the right. Hope you guys are enjoying is probably the wrong word, but hope your first days of quarantine are going okay. Please let me know. This is now I'm set up in my house, so I believe this should be a pretty consistent setup that I have. I tried to adjust the mic a little bit at the beginning because I think it was a little bit loud, but let me know if it was too loud, too quiet, if I was going too fast, if you want me to slow down, anything like that. As always, we are definitely looking for criticism, and as long as it's constructive, at least. Hope you guys have a great rest of your day, and hope to see/hear from you soon.